Start. Yeah, okay. Hi, good evening, guys. So today we'll be discussing a couple of questions on nuclei. Uh, let's start with question number one. The question reads out that an unstable heavy nuclei, okay, which is at rest. So this even nuclei is at rest, and it breaks down into two nuclei, which moves away with velocities in the ratio 8 is to 27. The ratio of the radii of the nuclei is, okay. So यहाँ पे इस क्वेश्चन में जो अपने को दिया है, यहाँ पे अपने को दिया है कि हमारे पास एक हैवी न्यूक्लियस है जो रेस्ट पे है इनिशियली, जिसकी वेलोसिटी हम मार्क कर सकते हैं 0। अब ये ब्रेक हो गया है बेटा के दो न्यूक्लियाइज में। लेट्स से द मास ऑफ द फर्स्ट न्यूक्लियाई इज m1 and mass of the second nuclei is m2. Also, the question reads out that both of these nuclei, they are moving away. Okay, so we can easily write, okay, let's say this is moving with velocity v1 on left side and m2 moves with velocity v2 on right side. Okay, now we can make use of conservation of momentum. Conservation of momentum, the initial momentum of this nucleus is 0. Okay, so final momentum will also be 0. If we'll take rightward as positive, then this velocity will be taken as negative. So we can easily write down the momentum of first, which is minus of m1 v1 plus momentum of second, which is m2 v2, and this is equal to 0. Now from here we can easily write down that m1 v1 is equal to m2 v2. Now from here we can write down m2 over m1 is equal to v1 over v2. Now in question, the ratios of velocities are already given, which is 8 by 27. Okay. Now we can easily write down that m2 by m1 will be equal to 8 over 27. Okay. Now we know mass of the nuclei can be written as volume of the nuclei and density of the nuclei. Okay. Now we know density of the nuclei is independent on the type of the atom. So density for both of these nuclei, M1 and M2, will be same. Okay, so we can write down that M1 is equal to, because we have to assume that these nuclei are spherical in shape. So we can write down 4 by 3 pi, and let's say the radius of this nucleus is R1 and radius of this nucleus is R2. So we can write down 4 by 3 pi R1 cube into density, and M2 can be written as 4 by 3 pi R2 cube into density. Okay. Now from this, we can easily write down the ratios M1 or M2. Now we need M2 over M1. So M2 over M1 can be written as M2 over M1 is equal to 4 by 3 pi R2 cube into density over 4 by 3 pi R1 cube into density. Okay. Now from this, we can easily find out the ratios. M2 over M1, this ratio will become R2 over R1 whole cube. Now we'll make use of this, and from these two equations we can easily write down that R2 over R1 cube, sorry, R1, this is R1, R1 cube is equal to 8 by 27. This will give us that R2 over R1 is equal to 2 over 3, and ratio of R1 over R2 will become 3 is to 2. Now option C is the right option. So we have 3 is to 2, which is the ratio of the radii. Now let's move to question number 2. Now in this question, we need to find out the binding energy per nucleon It's not the total binding energy, but we need to calculate the binding energy per nucleon. So we have to find out binding energy per nucleon. Okay. Now, what do you mean by nucleon? Nucleons are simply number of neutrons plus number of protons. Okay. Now, and the atom given is tin, which is SN120 50. So let's find out the number of nucleons and neutrons and proton here. So for given nuclei SN 120 50, A is the atomic mass and Z is the atomic number, which is 50. And this Z atomic number will give us the number of protons here. So number of protons is nothing but that is Z. Z is equal to 50. And number of nucleons are the total number of neutrons and number of proton, which is 120 here. So this is 120 and 120 is equal to number of neutrons plus 50. Okay, so number of neutrons will be 120 minus 50, which is 70 here. Okay. Now we know the number of neutrons and number of protons in this given nucleus. We'll make use of these two and we'll find out the total mass of the 50 protons and total mass of the 70 neutrons here. Okay. So total mass, which we call theoretical mass, the total mass is 50 times of mass of a proton, which is 1.00783, and 70 times of mass of neutrons, which is 1.00867. Okay. And this is the mass is given is in atomic mass unit. Okay, U. So this whole mass which we will calculate here, this is in U. Okay, this mass will be in U. Also, the mass of the tin nuclei, which is given here, the mass of the tin nuclei is 119.902199 atomic mass unit. Okay. Also, it is given that one atomic mass unit is equal to 931 mega electron volt. Now we know the binding energy. The total binding energy is mass defect delta M into C square if mass is in kg or in gram. Okay. But if mass is in atomic mass unit, which is given here, then binding energy will be simply 931 into delta M, but delta M in U. Okay, mega electron. Now delta M we can calculate from here. So simply delta M is the total mass minus the mass of the tin nuclei. Okay, this we can calculate. We can calculate this from these two equations. Okay, and after calculating this, we will directly put the value of delta M here. And once we'll calculate these, we'll be getting the binding energy, the total binding energy. Okay, the this mass difference. But we need to calculate the binding energy per nucleon. Okay, so let me just write down binding energy per nucleon here. Okay, which will once we'll calculate, then this total binding energy divided by the number of nucleons. Number of nucleons are 120, and once we'll do all these calculations, we'll be getting the answer is 8.5 mega electron volt. So D is the right option here. Okay. Yeah, it's going to be a lengthier calculation, but that's what these questions are. Okay, so now let's move to the question number 3. At a given instant, set T is equal to 0. Two radioactive substances A and B have equal activities. Okay, so let's say the question reads out that let's say we have two radioactive substances A and B, and at T is equal to 0, their activities are equal. So at T is equal to 0, the activity of A, let's say the activity of A at T is equal to 0 is R A naught, and this is equal to activity of B at 0. Okay. The ratio of their activities RB over RA after time T itself decays with time T is equal to e raised to power minus 3t. So the question, it's given in the question that after time T is at time T, their ratios of the activities, which is RB over RA, is e raised to power minus 3t. Okay. We need, if the half-life of A is natural log 2, so this is also given that T half of A, which is natural log 2, we need to find out the half-life of B. Okay. So we need to find out half-life of B here. Now, as we know, the half-life is simply T half is equal to natural log 2 over decay rate for a radioactive substance, lambda. Okay, so this means if we have to find out T half of A, then T half of A is simply natural log 2 over lambda of A, and T half of B will be nothing but natural log 2 over lambda of B. Okay. Now let's write down the activities of A and B at time T. So RA can be written as activity of A at 0 time and e raised to power minus lambda A of T, and RB can be written as RB at 0 time and e raised to power minus lambda B, sorry, lambda BT. Okay. Now let's find out the ratio of both of these. This will cancel because both are equal. It's given in the question. Now we can write down that RA over RB is e raised to power minus lambda AT over e raised to power minus lambda BT. Okay. But the ratio given is RB over RA. Okay. That is e raised to power minus 3t. So this means RB over RA can be written as e raised to power minus lambda bt over e raised to power minus lambda at. This we can easily write down minus of lambda b minus lambda a into t. Okay. Now let's compare this function with this. So we can easily write down if bases are equal, then their exponents will also be equal. So from here we can easily write lambda b minus lambda a is equal to 3. Okay. Now from here it is also given that t half of a is natural log 2. So let's put it here that natural log 2 is equal to natural log 2 over lambda a. Now from here we'll get lambda a is equal to 1. Now putting this value here, we'll be getting lambda b is equal to 4. So therefore, the half-life of B can be written as T half of B can be written as natural log 2 over 4. Okay. So from this given option, C is the right option. Okay. Now, here is another one which reads out a nucleus of mass M. Okay. So we have a nucleus of mass M that emits gamma ray photon. So this is emitting gamma ray photon of frequency nu. The loss of internal energy by the nucleus is, take C is the speed of electromagnetic wave. Okay. Now this is like we have a nuclei which has mass m. Okay. And this nuclei is emitting a gamma photon of, and frequency is given as nu. Okay. The loss of internal energy. Okay. So the first thing, let's write down the internal energy here. The internal energy can be written as, for this nuclei, the internal energy is equal to mc square. Okay. Yes. Now from here we can write down the loss. Loss can be written as, okay, this was the original energy. Now this energy, okay, it is converted into, now some of the energy has gone into the photon. Okay. So if the energy, the energy of the photon is EP, which is h nu. Okay. Now the loss of the internal energy of the nucleus is, okay, this can be written as the loss of the loss is the initial energy minus h nu. Okay. So this can be written as, if you take h nu common from here, the loss of the internal energy by the nucleus is, okay, ये एक क्वेश्चन है ना, इसमें कोई दिक्कत नहीं है, चलिए कोई नहीं, देख लेते हैं. So initial energy was mc square, and this is, sorry, this is the energy of the photon which is released h nu. Okay. So when it is releasing the photon, it is acquiring the kinetic energy as well. Okay. So the kinetic energy acquired was, we can easily write down, it is the momentum of the photon and this is the momentum of the nucleus. Okay. And both must be equal. So momentum of the photon can be written as, we can easily write h phi lambda, that is the momentum of the photon. Okay. And h by lambda, and lambda can be written as, from here, c by mu. So we can write down the momentum of the photon is h c by mu, which is h nu by c. Okay. And momentum of the um, of the nuclei can be written as under the root uh, under the root the 2 times of kinetic energy of the nucleus multiplied by m. Okay. And because initially this nucleus was at rest, so we can easily write down that the net initial momentum was 0 and final momentum is momentum of photon plus momentum of nucleus, and momentum of nucleus mode can be written as momentum of photon mode. Okay. So this can be written as so from here we can easily write down the kinetic energy of the nuclei is momentum of the nuclei square divided by 2m. Okay. Now from here we can write down the momentum of the photon. Okay. So and the momentum of photon we know that is h nu by c, and that is equal to the momentum of the nucleus. So the kinetic energy of the nucleus can be written as from this equation that we can replace Pn by momentum of photon square divided by 2 times of mass. Okay. And that is equal to uh, this can be written as h square nu square divided by 2mc square. Okay. Yes. So this is the energy, which is the kinetic energy of the nuclei. Okay. Now initial energy is mc square. Okay. And this is h square nu square by 2mc square. Okay. Now loss can be written as this loss. So the loss of, let me just clean it out. This loss can be written as delta E is equal to the kinetic energy, which is uh, now this can be written out the photon minus h square nu square divided by 2mc square. Okay. So this can be written as h nu 1 minus h nu over 2mc square. Okay, from this given option, C is the option which matches the loss calculations. Okay, is that so? Loss. Oh, sorry. Sorry. The loss is actually the energy of the photon plus the kinetic energy. Sorry. So we need to find out the total loss. So this is asking the loss. Sorry, this is not this one, because the loss, because the overall energy which has been lost is actually some of the energy is getting transferred to the photon, and then some of the energy actually has gone into the kinetic energy of the nucleus. So that's why the total loss is the energy of the photon plus the kinetic energy of the nucleus, which is h nu plus h nu h square nu square divided by 2mc square. So this must be this one. So D is the right option. Okay. Now let's move to question number 5. In this question, an X-ray tube is operated at 1.24 million volt. Okay. The shortest wavelength produced by the produced photon will be. Okay. So okay, the thing is, so if we remember, how X-rays works. So when we accelerate, the electrons and bombard on a metal, and when they get deaccelerated, they emit photon which are in X-ray region, and if we remember the curve, the intensity versus lambda, then this curve of continuous X-rays looks like this. Okay. And there are some of these things you will see if you remember. These are these kind of things which we call characteristic X-rays. And this wavelength is known as lambda cut off. Okay. Or this shortest wavelength which can be produced while we are producing the X-rays. Okay. And this cutoff wavelength, it only depends on the accelerated potential. Okay. Here in this question, the accelerated potential given is 1.24 million volt. Okay. Now simply we can write down that the is energy of the photon is 12,400 over, or it is asking in nanometer. So we will make use of 1240 over lambda in nanometer. Okay. And this energy is given in electron volt. Okay. Now, because the electron has been accelerated by a potential of 0, and this is plus b, of 1.24 into 10 raised to power 6 volt. Okay, this is the potential applied. And this electron has been accelerated by this. So the energy acquired by this electron is 1.24 into 10 raised to power 6 E volt. Okay. So this means if this energy, we will put it here, then we'll get simply the lambda photon. Okay. So 1240 over lambda in nanometer is equal to 1.24 into 10 raised to power 6, because both are in electron volt. So lambda in nanometer can be calculated as 1240 over 1.24 into 10 raised to power 6. This can be written as 1240 over 124 into 10 raised to power minus 4, and this will give 10 raised to power minus 3 nanometer. Okay. So the given, out of the given options, the right option is B here. Okay. Which is 10 raised to power minus 3 nanometer. Let's move to question number 6. Again, this is based on radioactivity. Two radioactive substances X and Y originally have N1 and N2, N1 and N2 nuclei respectively. So this means at T is equal to 0, the number of nuclei of X and X at 0 is N1, whereas Ny at 0 is N2. Nuclei respectively. Half-life of X is half of half-life of Y. Okay. So this is given that T half of X is half of T half of Y. This is given. Okay. Now after, or it's not there, if it's actually 3. After 3 half-lives of Y, okay, so this means we are looking for a time which is 3 times of T half of Y. This means in time T, there are 3 half-life of Y has been consumed. So this means 3 half-life of Y, the number of nuclei of both are equal. The ratio of number of nuclei of both are equal. The ratios n1 by n2 is equal to. Okay. So number of nuclei remaining is equal to the number of nuclei at 0 divided by 2 raised to power n, where n is the number of half-life consumed. Yeah. Now we know that the t half of y is equal to 2 times of t half of x. Okay. So if in t time 3 half-life of y have been consumed, then in the same time we can write that there are 3 into 2 into t half of x, means 6 half-life of x has been consumed. Okay. Now this is simple. It is also given that after time t or after 3 half-life of y, the number of nuclei for both are equal. So simply we can write that nx at t, which is nothing but nx at 0 divided by 2 raised to power n. N is the number of half-life consumed, which is 2 raised to power 6, and ny of t, which is ny at 0 divided by the number of half-life consumed, which is 2 raised to power 3. And this is nothing but this is n1 and this is n2, and this is n1 divided by 2 raised to power 6. This is n2 divided by 2 raised to power 3. And it is given that both nxt and nyt both are equal after time t. So this means these two values are equal. So n1 over 2 raised to power 6 is equal to n2 over 2 raised to power 3. Now we need to find out the ratio of n1 and n2. So this gives us n1 over n2 is equal to 2 raised to power 6 over 2 raised to power 3, which is 2 raised to power 3, and ratio is 8. 8 is to 1. Okay. Option A is right. Let's move to the next question. In this question, the Q value of a nuclear reaction. Okay, so there is a nuclear reaction whose Q value is given Q, and the kinetic energy of the projectile particle Kp are related as. Okay, so let's first understand how a nuclear reaction works. So if we look into, then let's say we have a, a target nuclei like this, and then we have a projectile P on it, okay, which is coming up with some kinetic energy, and target is initially at rest. This will, both of these, they will give, let's say these are the two resultant nuclei or the product of these two reactants. Then let's say this is X and this is Y. So we can easily write down that Q value of this nuclear reaction is nothing but the kinetic energy of the reactants minus kinetic energy of the product side, which is projectile plus reactant. So this is nothing but this is kinetic energy of X plus kinetic energy of Y minus kinetic energy of projectile plus kinetic energy of target. And we know that the kinetic energy of projectile target here is 0 because that is at rest. Okay. And this is, let's say, Q. So we can easily write down that Q is equal to Kx plus ky minus kp, okay, projectile, and this will come out here. Q plus kp is equal to kx plus ky. Now we know that kinetic energies, they cannot be negative. So this kx plus ky must be greater than 0. This implies q plus kp must be greater than 0. Okay. One of these options must be greater. So let's say if this is greater, then we can write D is the right option. Okay. And if B is given Kp plus Q is greater than 0, then we can take that as 0. But it must be Kp plus Q must be greater than 0. Okay. Now number 8, two lighter nuclei combine to form a comparatively heavier nucleus by the relation shown below. So, okay, there is a nuclear reaction which is taking place, and two lighter nuclei, they are actually combining together and they are forming a heavier nucleus. Okay, the binding energy. So here, please note down binding energy per nucleon is given, which is 1.1 mega electron volt, 2 times of 2x1 and 4y21r. Okay. So looks like again an error. Binding energy per nucleon for this is this, and for this is 7.6 mega electron volt. Okay. Now, respectively, the energy released in this process is, okay. Now, the given equation is 2x1 plus 2x1 is equal to y4. Okay. Now, here we know the binding energy. Energy released. So energy released is simply can be written as, sorry, this is 2. Energy released in a nuclear reaction is binding energy of product minus binding energy of reactant. Okay. Now, on product side, we know that we have 4 nucleons and binding energy per nucleon is 7.6 mega electron volts. So simply we can write 4 into 7.6. Whereas on the reactant side, we have 2 nucleons here and 2 nucleons here. So this can be written as 2 times of a binding energy per nucleon, which is 1.1, and this will give us 4 6 24 4 7 28 30 30.4 minus this will give us 4.4, that will give us 26 mega electron. Okay, so this answer is 26 mega electron. Now let's move to the question number 9. Again, from radioactivity, two radioactive elements A and B initially have same number of atoms. Okay. So at T is equal to 0, it is given at T is equal to 0, N naught A is equal to N naught B. Okay. The half-life of A is same as that of half-life of A is same that as of average life of B. We know half-life of a nuclei is written as natural log 2 over decay rate of that nuclei, lambda. Okay. So let's say for A, if we have to write down, then that is lambda A. And we know the average life, T average of a nuclei In this case, let's say it's B, that is simply 1 by the decay rate, 1 by lambda B. Then choose the correct relation from the given options. now, now it is given that half-life of A is same as of average life. So this is given that natural log 2 of lambda A is equal to 1 by lambda B. Okay. Then so it's much easier that lambda A is equal to lambda B natural log 2. So simply cross multiplication will lead to the right option. It's C in this case. Okay. Now let's move to question number 10. If the binding energy of ground state electron in a hydrogen atom is 13.6 electron volt. Okay. So binding energy, let's say this is the hydrogen nuclei and this is the hydrogen atom and the electron is in ground state. Okay. So to remove this electron, we need to supply 13.6 electron volt and that's what is the binding energy of this electron with the nuclei of the hydrogen. Then the energy required to remove the electron from the second excited state of lithium 2 plus. Okay, so let's first understand what do we mean by second excited state. So second excited state means if n is equal to 1, then this is the ground state. N is equal to 2 means first excited state. N is equal to 3 means second excited state. Okay. Now this we have to do for lithium 2 plus. Okay. Now lithium 2 plus, this means it has only single electron, but that electron is present in the second excited state, and we need to uh, then the energy required to remove. So we have to find out the energy required to remove this electron. Okay. Now energy required is 13.6 Z square by N square. Okay. Now simply this E is 13.6. Z is the Z is the atomic number of lithium. Atomic number of lithium is 3. So Z is equal to 3. So 3 square divided by N. The second excited state again that is 3. So this will cancel out and energy required is 13.6 electron volt. But we need to mention the energy in x into 10 raised to power minus 1. So this E as per the question is x into 10 raised to power minus 1 electron volt and this must be equal to 13.6 electron volt. Okay. Now x is 13.6 over into 10 raised to power 1 which is 136. So the value of x is 136. Good. Yeah. Thanks. Thanks for your time.